Well, hello everybody. My name is Steve Nightingale, and I'm going to be running a project this year which is entitled Which Road to Zero? Balancing Electricity Supply and Demand. The problem we're talking about addressing here is the fact that burning fossil fuels produces gases in the Earth's atmosphere which trap the sun's heat. This is known as the greenhouse effect, and this process makes the Earth warmer and causes significant change in weather patterns. And you will have seen and heard that this has been widely reported over recent years. The reaction by the UK government was to introduce their Road to Zero strategy in July 2018, with the idea that we reach the net zero emissions by 2050. And the ambitions of this strategy are that at least 50% and as many as 70% of new car sales and up to 40% of new vans will be ultra-low emission by 2030. And in January this year, the government set out some additional interim goals. The first was a reduction in emissions of 45% by 2030, which is basically the original target, a reduction of at least 80% in Scope 1 and Scope 2 emissions, a zero carbon emitting fleet of cars and vans by 2027, and a zero carbon emitting 4x4 fleet no later than 2030. Now, Scope 1 that I mentioned covers direct emissions that are owned or controlled by a company, and Scope 2 covers indirect emissions which are a consequence of the activities of the company, but they occur from sources not owned or controlled by it. So the result has been that we've now had increased use of acceptable green energy, for example, wind and solar. However, the intermittency of these technologies and other sources of electricity produce a very strong demand for efficient, cost-effective, high-capacity energy storage and distribution systems. And this, of course, in turn produces increasing requirements for rapid charge and discharge cycles of energy storage systems, for example, for the ultra-fast charging for road transport at service stations. So the project has a technical and a financial side. The technical side is to identify and select the optimum established and proven approaches for generating, storing and distributing electricity, both on a small and a large scale, and determine how these can be best applied to achieve the UK government's targets. And on the financial side, you need to determine the cost of implementing your selected approach. So here's the project again, just to illustrate what I'm talking about. So on the electricity supply side, you've got electricity generated by wind farms, by nuclear energy, by solar energy farms, by hydro schemes, which tend to be more prevalent in the north of England and Scotland. And then, of course, associated with that is storage of energy from intermittent sources that don't necessarily generate electricity when you need it. And then there's the demand side, where you have demand from transport, industry, businesses, homes, etc. And so it's being able to make the demand and supply balance. Now, I'm sure you're all familiar with wind farms. They're all over the place these days, and you see a lot of them at sea, where it's a better approach from the point of view of the wind blows more consistently, but it costs more money to maintain these systems because of the salt spray. There is also an issue to do with land where you can put wind farms to generate enough electricity. And the next option, of course, is solar energy. And you see solar energy farms around in the same way you do wind farms. And also you see solar panels on houses and industrial premises and hotels, much more than you see wind farms. Now, when we come to look at the storage, an obvious storage medium, because it's a very well-developed technology, is to use lithium-ion batteries. And Tesla have done this, and in September 2016, they built a 100 megawatt storage system in Hornsdale, South Australia, And this has worked extremely well. And of course, it's based on the lithium-ion technology that Tesla use in their batteries. The issue with lithium-ion batteries is they're well proven, they're used in cell phones, laptops, all sorts of other equipment, and they have a high energy storage per unit volume. But there is this issue of a finite supply of lithium, and that lithium is sourced from countries such as the Democratic of the Congo, where the way it's mined and the staff are looked after is rather poor. But there are other types of battery that one can consider. One is the sodium sulfur battery, which is well proven, being deployed for many applications worldwide. There are a list of key manufacturers of this type of battery. One of the disadvantages with it is that it runs between 300 and 360 degrees C, and it doesn't have as high capacity, higher capacity per unit volume. So it's a good solution for non-mobile, i.e. static requirements. One of the issues with lithium-ion battery is that after a certain number of charge-discharge cycles, it tends to lose its storage capacity and it doesn't hold its charge as long. And one of the main reasons for that is these dendritic growths that occur on the electrodes. And eventually they can end up touching, and they provide a conducting path within the battery. And so what you find is after a couple of thousand charge-discharge cycles, the battery's performance is significantly degraded. So a solution to that is that you have liquid electrodes, so the opportunity of developing dendrites is impossible, and you're constantly renewing the electrodes because they're in a liquid state. And one battery is the one produced by Ambri, and this uses calcium and antimony electrodes. It uses a simple calcium chloride salt electrolyte, and calcium is readily available as it's the fifth most abundant element in the Earth's crust. Another method you could consider for energy storage is to have electrolyzers placed where you've got wind and energy storage systems, and as the electricity is produced, you use it to run an electrolyzer to split water into hydrogen and oxygen, and you store hydrogen. You could store the oxygen too, but hydrogen is relevant to fuel cells, and you store the hydrogen under pressure for when it's needed, and then when it's needed you essentially run a fuel cell, a hydrogen fuel cell, in order to generate the electricity. And here I've listed 3 different types of fuel cell. Fuel cell technology is well proven, but it's not the best way to run, for example, an electric car, because apart from the complexity of it, the volume of hydrogen required means that you need a fuel tank that's about 5 times the volume compared with if you were running the car off petrol or diesel fuel. So it's interesting to look at where we are at the moment. And this listing here shows the percentage share of electricity generation by fuel. So in 2023, and the figures have changed slightly but not a lot for 2024, coal accounts for about 1.5%, gas, that's natural gas, 34%, nuclear 14.5%, and renewables, of which wind and solar are the dominant ones, 45.8%, and others such as biomass at 4.2%. So we've made significant progress over recent years in the greater use of renewables, but my opinion is that at the moment we went rather too far in building too many wind farms and too many solar energy farms, and we should have spent a little less money on that and rather more on being able to store the energy, because you find that the installed capacity of a wind or solar energy farm is not met anywhere near by the reality of the situation, such that in the end only 25% typically of the installed capacity of a wind farm is reached throughout the year, and about 17% of a solar energy farm. So that's the project, and I'd just like to comment on a few other things in preparation for starting this. and that is to point out this project's a systems engineering project, a more of a top-level project, and it will draw on many aspects of engineering that are common to all disciplines. So it doesn't really matter which discipline you come from, although I accept that for some disciplines you may be using more of your general engineering rather than anything specific. I suggest that you make sure you know how to chair a meeting and take proper formal minutes, not just notes. I will send out some notes I've written on this to help you with that before we actually start. And then when it comes to finding out about different technologies, I suggest you check out what information sources you've got in the library. Don't just rely on online resources. And also go and speak to people in this university that run different departments, because you'll find you'll be able to get a lot of information from experienced people in the different departments that have specialised in certain technical areas. I also suggest that you read the technology sections of quality newspapers like the Times and Telegraph, and that you also read the house journals of certain organisations like the Royal Academy of Engineering, that publishes a magazine called Ingenia, the US Institute of Electronic Engineers, that publishes a magazine called Spectrum, the Institution of Engineering and Technology, which publishes a magazine called Engineering and Technology, and then the Institute of Physics, which publishes a magazine called Physics World. All those are very good sources. I think it highly likely you'll have many of these, if not all of them, in your library, and suggest you have a read through those. You can, through a search, look for articles that have been published in the past. There have been many published in Ingenia in the past, and the Royal Academy of Engineering are very helpful in telling you which particular edition a certain article on storage, for example, was published. So that's it. So thank you very much for listening, and I look forward to seeing you when we start the projects. Thank you very much.